Okay, I can see your screen.
Okay. Yeah, thank you. So it's a real pleasure to have you all for the COMET meeting. I hope you enjoy like I do. So today I'm going to present some of the work we have been doing in the Fuego volcano for the past month. The first time I had the opportunity to present this work, like using TanDEM-X to measure pyroclastic flow, source location, thickness, and volume. And I want to acknowledge my co-author because it's very multidisciplinary works and with different expertise. And as you may know, Bristol has been engaged and on working on Fuego volcano for a long time now with Matt Watson and others. So today, yeah, I'm going to present, okay, why it's important to forecast and study pyroclastic density currents. Because first, it's a common hazard during explosive eruption. And also it has a high human cost. So you can see here that it's count for 33% of fatalities related to volcanic eruption. And if you see the top three deadliest eruption in the 21st century, you can see that Fuego in 2018 and Merapi in 2010, the casualties were caused by PDC. It also have an high economical cost due to the evacuation. So in Agung in 2017, there was 140,000 people evacuated. In Merapi, over 300,000. How you can understand and forecast these pyroclastic density currents? First, you need to understand the flow processes, and you do that by historical records, the collection of observation as the distance, the thickness, and the volume, and also the simulation of the flow. So the simulation of the flow take the volume as an input and give you the run-out distance, and you can run a series of multiple simulation to get a better grasp and to constrain the hazard maps in the evacuation zone. So here is an example in Merapi of a flow model and the hazard zone corresponding. So very important to collect data and to have a better constraint on the volume of this flow. And this is what I'm going to focus today. How you can calculate flow thickness and volume. The common method is to do field observation that give you accurate measurement, but it's sparse measurements because it depends on the accessibility. Usually you have a dense measurement close to the edge of the flow, but close to the vents on high topography is very difficult to have a field observation. That's why we also look at remote sensing and INSA in particular. In this case, you have a dense measurement with a good spatial resolution, but the uncertainties can be high due to some vegetation, some processing aspect, and also the high topography. So today for this talk, I'm going to use the TanDEM-X bistatic interferometry. So this mission was launched by the German agency in 2010. It has a bistatic mode. So the bistatic mode is acquisition of the same area at the same time. And it's very relevant and useful for topographic generation of digital elevation model because the phase difference is only dependent on the orbit and the topography. You don't have atmospheric signal or deformation. For the DM, you expect to have so the resolution of the data is 2 or 3 meters. Usually you calculate a DM at 5 or 10 meters. And then the vertical accuracy you can have is below 2 meters. One of the aspects interesting is this is an X-band sensor. So keep aware that the X-band we model at the top of the tree as a result of the digital elevation model, and I will come back to that later in my talk. So TanDEM-X data have been used quite a while for mapping and deriving flow thickness and volume on effusive eruption. So here you have an example of different volcanoes where TanDEM-X were applied in Kilauea, Nyamulagira, Ventador, and Colima. And this is that has been useful and that proved the efficiency of the method for lava flows. But what about pyroclastic flow and pyroclastic density currents? So you can see the main problem is the topographic changes that you have in these different contexts. So here in Hawaii, you see that the topographic change you have is just the empilement of lava flows. And it's kind of easy because you have the edge of the flow. It's very easy to discriminate the topographic changes. When in a pyroclastic density current, you have different aspects and different source for the topographic changes. So you can have like small changes due to the ash fall. you have the surge deposit on the overbank and some flow deposit on the incisive valley, and also the removal of the tree, we'll see later, has an effect on the topographic changes. So it's quite difficult, but we wanted to test the method for the Fuego eruption in 2018. So it was an eruption started in the 3rd of June 2018, explosive eruption. So usually Fuego volcano has strombolian activity with few pyroclastic flow that you can see here in the past years that reach about 6 kilometers from the summit. And here you see that this event in 2018 reached double the 12 kilometers, and it was a particular deadliest eruption with above 446 people, and unofficial counting is more like 3,000. So very deadly eruption with a very long pyroclastic density currents. And then, so we use some Sentinel-2 data, optical imagery, to look at the flow and the mapping of the different facies of the flow. So you can see here the different collapse, transitional, the overbank, and the channelized flow, and some surge, some ash cloud surge here on the eastern side. What I want to point here also is it's also always good to remember like the link between fatalities and awareness. So you can see here a map with two different locations that were affected by the pyroclastic density current. So the first one is La Réunion Golf Resort. And in this area, there was a high awareness because there was some station for the monitoring of the volcano and current visit of the local volcano observatory. So there was some evacuation during the event and no fatalities recorded. When in San Miguel de los Lotes, which is only a few kilometers from that golf resort, there was a low awareness, late evacuation, and high human costs. So I think it's really important to emphasize that and to keep that as a reminder for future events. So now that we have the mapping of the different parts of the flow, we want to know with TanDEM-X if it's possible to look at the topographic changes associated with these events. So what we are looking now is just, so I generate a DEM with a spatial resolution of 10 meters, and then I make difference between different periods. And here we are looking first the post-eruptive, so after the eruption, a very short DEM difference between August 2018 and September 2018 that give you kind of a sense of the accuracy and the certainties of the method. So you expect no topographic change on the flow. And here the histogram here in red show the distribution of topographic change inside the flow at this time, and give you like a mean center to 0 and a standard deviation about 5 meters. If you look at the same for the co-eruptive, so during the eruption, you can start to see some topographic changes, mostly some negative, so blue area on the proximal section, and some positive topographic change on a distal section that could be associated with the accumulation of materials. And you see here on the distribution in red that you are more spread distribution that show you the erosion and negative topographic change on this part and some deposition on the other. So now I'm going to zoom first on the distal section to show you how it looks like and compare to the Sentinel data. So here you clearly see this channel flow, channelized flow with topographic change, positive topographic change up to 25 meters. And then on the overbank around this positive change, you see negative, quite a clear negative changes here on this part of the flow, and that correspond to some vegetation area. So we expect, we think that this is due to some loss in vegetation. And if you look at photo pictures on the field, you can see this channel with some deposition here on the middle, and here you see the tree with some loss in the leaves over the trees that could explain why we record these negative changes on the overbank. Then I move on to the proximal section, and you see here on the proximal that you have a large negative changes on this about 1-2 kilometer length, and you see that these changes is up to 68 meters. So we believe that we are seeing here like the collapse of volcanic material close to the summit, and we can look at pictures before and after the eruption, and we see here this material that was present in 2017 completely disappear, and you see this large collapse and loss of material after the 2018 eruption. So we look at back in some of the data in 2015, and we remarkably notice the same kind of extension here on 2015 for a small eruption. So during this October 2015, there was a small event just close to the Barranca Las Laras, but you can see in the profile that we have kind of a recurrent collapse, about 30 meters occurring at the same location. So now we look at the volume, we derive the volume from this thickness map, and we were like surprised, amazed that the erosion volume, the negative volume, kind of balance the deposition volume. And we believe this is due to a bulking effect. So the bulking is the class incorporation process that increases the flow volumetric solid fraction. So you see here an example on the Tungarua 2006 eruption. So you have an incorporation of material due to the frictional stress on the bed here. Now incorporate materials, increase the flow mobility, and can speed up and increase the runout distance by up to 20% in this case. And this is mostly driven by slope above 25 degrees. So we try first to look at the different mass balance for the different facies. So this is we decompose the volume per facies, and we see an increase of deposition from proximal to distal distance, and at the same time a decrease of the erosion volume from proximal to distal. And we want to know at which slopes this transition occurs between an erosion and a deposition in this flow. And we are looking at that by plotting the mean slope for the different facies as a function of the net volume. And we see this transition, of course, there is large uncertainties, but taking the mean slope, we see about around 29 degrees of the slope transition between erosion and deposition. So now I just leave up with my conclusion. We believe that Fuego eruption in 2018 show a bulking process with some increase in the flow mobility that can explain this increase in runout distance. And I think this TanDEM-X data is very useful and can be applied to other stratovolcanoes to quantify the thickness of the deposit, but also more importantly to look at this accumulation collapse of volcanic materials at the summits, as they are the source of the PDCs for most of the eruption. Okay.
Fabien, thank you very much. Excellent presentation. Do we have any questions from the floor? If not, I'll kick it off. I mean, Fabien, assuming you can get the TanDEM-X data pre and post event, how long does it take you to make your DEMs and do the DEM difference? How involved a process is it?
It's quite quick. I mean, it take less than an hour to get to derive a map. A map thickness. I think the longer time that you cannot maybe sometimes do it for monitoring in real time is the time you can access the data. I mean, how long the data are online. But for the processing, is quite a quick time. It could be definitely useful for monitoring.
And have you ever considered using optical data like Pleiades tri-stereo as pre or post data for your comparison?
We haven't. I know Pleiades is kind of difficult sometimes in this kind of environments and during the eruption with gas and the emission. This volcano tend to have a large column and ash cloud, so sometimes difficult to get nice acquisition of Pleiades in this area, I think.
Okay. I don't see any more. Oh, hang on. Tams and Mallory's just coming in for a question. In terms of operationalizing this, what are the key ground data you would like to have?
Key ground data for validation, I think measurement like some punctual GNSS or leveling measurements, quite hard to do in this kind of flows because of accessibility. But down in the deposition area, I think having a better constraint on the deposition on the field and compared to the TanDEM-X data will be a nice thing to do first, yeah.
There's a question or a comment from Loco. For risk maps, the probability of inundation by a PF is the most important. This method is feeding important information to the flow models. Do you have any comment on that, Fabien?
Yeah, I think, constraining the volume of these PDCs is kind of very important for the simulation, for the modeling input, and I think is completely true that we need maybe more this kind of data in exploring different volcanoes and different flow to see how we can improve our knowledge about this constraint for flow simulation, definitely.
And from Valerie Cole, how would you combine these results with models of deposits?
For the deposit, I think from TanDEM-X data alone, it's quite difficult to have I mean, if she's talking about flow deposit or ash deposits, can you precise, Valerie, if you talk about ash deposit? Because, okay, flow deposits, I think, I think it's comparing, so because of the TanDEM-X data, we get an accurate measurement of thickness along the flow. And also this process of what I showed, this collapse, this bulking effect is not really incorporated in the model right now. They are assuming a kind of an initial volume, but trying to complexify the model and having this incorporation of materials as the flow is progressing from proximal to distal. And that's increasing by large amounts the runout distance. So if we kind of complexify or adding these physical processes into the simulation, I think we can get a different answer and kind of have a better constraint on these events that we've seen in Fuego in 2018.
And there's a follow-up from Tamsin to her question that she was thinking of things like harvesting Twitter photographs and using them for small-scale DEM generation, which I know some people are trying to do for coastal landslides, coastal erosion at the moment as well.
Okay, I haven't think about that, but yeah, why not like gathering information? So we had a couple of photos from, so we are lucky to have like a field trip every year from Bristol University going to the field in Fuego, and they were there in March, I think a few months before the eruption. So we gather some photo from them. But yeah, a systematic way to collect information and get more information and pictures, photo from the deposits and trying to derive some quantification from that will be nice to investigate for the future. Yeah.
Okay. And we've got a final question from Yasser. I think you touched on this in your presentation, but you said that TanDEM-X is giving the top of tree height. Does this make any issue for your processing?
Yeah, so it's true. I mean, it's basically we think that this negative, that's why we get negative topographic change on the overbank is mostly the top of the trees before the eruption, and then when the leaves are removed after the eruption during the event, we get the base of the trees, and that's caused. So it's also nice to kind of derive the destruction and the destruction of the vegetation and these processes that occur on the overbank. Of course, it's quite complex to derive volumes because some trees stay up, some other like may have been burned, and so try to derive a volume balance from this negative topographic change is an issue. But for future mission like TanDEM-L in L bands could provide the base of the trees and make more like accurate measurement on that, I think.
Yeah, I look forward to that data set, definitely.
Yeah.
I would just like to acknowledge the three presenters we had in this session. It's extremely difficult to give a presentation when you can't see the audience and can't see any reactions. So I'd like us all to thank in whatever way we can the three presenters, either by doing your round of applause and thumbs up or by turning on your cameras and giving a wave, whatever you'd like to do. I can see lots of claps coming on screen. So well done to Alex, Isabel and Fabien for fantastic presentations, especially given the circumstances.
Thank you.
I see we have a lunch break now until 2:45. I don't know if Tim or Charlie wants to come in and give some comment on housekeeping for the next session, or do we just come back at 2:45?
Well, I would